So here, looking at our flow chart again, is it symmetrical? No, it's going to be polar. Automatically, if we have things that have lone pairs on the central atom, which ones are the ones that have lone pairs on the central atom? Which shapes? Which one? Bent is one of them. So bent would be in this category, definitely. And what's the other one that has lone pairs? It's automatically polar because it throws off the symmetry. Which one? The pyramidal one, yes. Okay. So both of these automatically fall in the polar category because they have lone pairs on the central atom. Now, the other ones you would look at, is it symmetrical? Is if the ligands, the ones that go around the central atom, if they are different, they would also fall in this category. So if you don't have lone pairs on the central atom, and the ligands are different, okay, then it's also going to be polar. So are all the ligands identical? This is yes, then it's nonpolar. If all the ligands are not identical, which would be no here, they're going to be polar. So looking for the attachment ones for the ones that do not have lone pairs. Okay? Also down here it helps identify the shapes, again, just like you had the chart on your other ones. Talking about the ligands, the ones attached to the central atom, the total number of atoms in the molecule itself, and your lone pairs give you the shape, and then it tells you whether or not it's polar or nonpolar. It's a good thing to follow as you're trying to do this worksheet. So now, if we're going to look up here at the formula itself, F2, if we can't remember, we can always draw the Lewis dot structure, but here we only have two F's in it. Therefore, are they identical? Yes, they are identical. So it's automatically going to be what? Nonpolar. Good. This one would be nonpolar. Yes. The ligands are the atoms that attach to the central atom. So in this case, we have carbon tetrachloride. Carbon would be in the middle. So the chlorines would all be ligands. Okay? That's what we would identify. The ones going around the carbon are the ligands. Now, looking at this one, that means carbon's in the middle, and then we have 4 chlorines attached to it. That means it's a total of 5 atoms. That would be 4 ligands, 0 lone pairs of tetrahedral. Is it going to be polar or nonpolar? Nonpolar, because the ligands are all the same. Very good. So this one would be nonpolar as well. Okay? I'm just going to do 1 or 2 more of this section to help you. Anybody want to choose a number, particular number to look at? 7. Let's look at 7. Okay. HCl. This one has 2 atoms. Okay. No ligands. It's going to be linear shape. 2 atoms. Are they different or the same? They are different. So if they are different, guess what they are? Polar. Okay. So this one down here, HCl, would be polar. If the atoms were the same, it would be nonpolar, but since you have an H and a Cl, they are different, it's going to be polar. Okay? Now let's look at this section down below. Here they actually give you the ball and stick models, which is helpful to look at, along with the formula. We just looked at this one, carbon tetrachloride. And you can see all of the ligands around the central atom are the same. There are no lone pairs, okay, as you see here. So that one would fall under this category. The 5 atoms, the 4 ligands, no lone pairs, the tetrahedral shape, okay. And we would determine this one to be what? This one would be nonpolar. Looking here at 13, let's go across to 13. What is automatically there that we can determine that is going to be polar? We see lone pairs here. These lone pairs, okay, that pushes them downward. It throws the symmetry off, and we're going to automatically be polar, okay? Those lone pairs make it bend shape. 2 lone pairs, 2 attached, bonded atoms, that's going to be bent shape, okay? Let's look at this one, 17. What kind of shape is that, first of all? It's not planar. Why wouldn't it be planar, though? What is there that doesn't make it planar? It pushes the other three downward. What's there, though, that makes it more pyramidal shape, pushing the other atoms downward? What is there, making it more, pushing it downward? That lone pair at the top. Okay, that lone pair at the top pushes the other three atoms downward, causing it to be pyramidal shaped. So therefore, this one would be what? Polar or nonpolar? Polar. Very good. Okay. Now we're looking here at a couple others. Let's check them out. Let's look at, say, this is a good one. Formaldehyde, number 15. Number 15 is formaldehyde. The central atom is carbon. We have oxygen and 2 hydrogens. Are our ligands the same? No, the ligands are not the same. So therefore, it's automatically polar. Good. This one would be polar. Very good. So that's the basic gist of how to do this one. You're going to now finish this one up for next class. Okay? So let's go ahead and move on to the intermolecular forces. Okay, so intermolecular forces. We're going to be talking now about the things that hold the molecules together. Like, for instance, when you have a glass of water that has multiple water molecules in there and they are stuck together somehow, making it, you know, a sizable amount of water in there. Okay? And what's doing it, that's holding it together, is specifically called hydrogen bonding, but we're going to address some of the other forces as well that hold things together. Okay? The first three up here are dealing with the ones that are for covalent compounds. Okay? Up here, we have dispersion forces. Dispersion forces are for nonpolar molecules or atoms. So if you have a noble gas that doesn't react with anything, it also has dispersion forces. Okay? Let's talk about what dispersion forces are. If I was like a molecule of methane, CH4, I have an electron cloud around my atoms, and around my molecule has a bunch of electron clouds, right? And let's say that she is also a methane, and he's also a methane. If I come close to them, my electron cloud's going to do what to their electron clouds? What do electrons do to other electrons? They do repel. Negatives repel each other. So if I'm standing over here next to her electron cloud, my electron cloud's going to have hers repel mine, and it's going to push the other direction. So my electron cloud will now go that way. This side of her is going to be partially positive now because most of her electrons are spending more time in the other direction. So what I did is created a temporary dipole. This side of her is slightly positive now, the other side of her is slightly negative. It's temporary because the second I move away, guess what happens? Her cloud goes back to being normal. Okay? So it's a very weak force. Very, very weak force. Everything does it. All atoms, all molecules will have dispersion forces because all atoms have electron clouds. However, some of the other ones will have other forces as well that are more predominant. That's what we say. We're looking for the predominant one because everything has dispersion. Everything will have dispersion because everything has electron clouds around it. Then we'll talk about some of the other ones that have more than dispersion. The next one, which would be polar molecules, they have dispersion, but they also have a more predominant force called dipole-dipole, and we call it dip-dip for short, by the way. And you can write dip-dip on your paper, and I won't take off for that because it's a lot to write dipole-dipole every single time. Okay? Now, before we get to that, I forgot to address one more thing about dispersion forces. Dispersion forces get stronger if the molecules get bigger. See right here, we have CH4 and we have CBr4. So methane and carbon tetrabromide. Carbon tetrabromide, those bromines are a whole lot bigger, right? They have about a mass of 80 each. They're bigger, that means their electron clouds are going to be bigger. If you have bigger electron clouds, you're going to cause a bigger dipole. So, if you have more mass and you're bigger, your dispersion forces will be a slightly bit stronger than something like methane, which is smaller and doesn't have as big of an electron cloud. So if you have two dispersion forces molecules to compare, you look for size. Who's bigger? The bigger one's going to be slightly stronger. Okay? Just so you know. That's noted right here, by the way. So you can go back over that if you have that pop up. Okay? Now we're going to be talking about dipole-dipole, which go with all the polar molecules. So these are the ones that already have a dipole in them. So one side of the molecule is partially positive, one side of the molecule is slightly negative. So for instance, this is a common one used, HCl. Remember, if we draw the dot structure, it looks like that, right? Which side of the molecule is slightly negative? Who's hogging and keeping the electrons closer to it? Cl is. So this side of the molecule is slightly negative. That means the H side of the molecule is slightly positive. Okay, creating a dipole. This isn't temporary, it stays that way. Okay? And therefore, the positive sides of the H will attract to the negative sides of other molecules, and the negative side of the Cl will attract to positive sides of other molecules. And we're going to draw an example when we get to number 2. Okay? Not last but not least, we're going to be talking about hydrogen bonding. And hydrogen bonding is a specific dipole type arrangement. Because hydrogen's so small compared to other atoms, it creates quite a huge dipole, and therefore it's stronger than just regular dip-dip or dipole-dipole. The thing is, though, hydrogen bonds, of course, have to involve hydrogen themselves. Okay, but there's only 3 types where it works. It has to be H with F, or an H bonded to an O, or an H bonded to an N. That's the only 3 cases where you have hydrogen bonding. And of course, the most famous one that we know of is which one? H2O, which is water. Okay? Water is the most famous of the hydrogen bonding because you know a lot about water. There you go. Now, these 3 here, these are your IMFs, or intermolecular forces, and they apply to covalent compounds. You do also have ionic bonds, because ionic compounds really are just a big lattice structure of positive, negative, positive, negative, positive, negative. Okay? Don't forget that those are metal, nonmetals here, or polyatomics involved, and they are super strong. They are way stronger than any of the IMFs, and that's why ionic compounds have the higher boiling and melting points. Super, super strong. So they're way stronger than any of the IMFs. We're going to be comparing all 4, though. The 3 we call forces. Ionic bonds are actually real bonds, but the other ones are forces between molecules. Okay? And here is the note. We go from weakest to strongest. Dispersion being the weakest, dipole-dipole, hydrogen, and then of course the strongest would be ionic bonds. So let's talk about some examples here. Using your knowledge of molecular structure, identify the main intermolecular force. Because we said, everything has dispersion. Water even has dipole-dipole, but its predominant one would be hydrogen bonding because it's the strongest out of the 3. So in water, the most predominant one would be hydrogen bonding. So we're looking for the intermolecular force in the following compounds. You may find it useful to draw the structures. Okay? If you want to, you draw the structures to figure it out. Once you have done the shapes over and over again, they start to become repetitive, and you're like, oh, I know carbon tetrachloride. Oh, that's tetrahedral. And it's got the same ligand, so it's got to be nonpolar. Okay? But if you're not to that point where you can recognize it, then draw it out. Like so. Right? Attach the ligands, count the electrons, put in the lone pairs. Like so. Okay? If you can't remember that, oh yeah, that's going to be 4 things attached, no lone pairs on the carbon, it's going to be tetrahedral, all the ligands are the same, this is definitely nonpolar, okay? If it's nonpolar, what force does it have? Dispersion, yes, so what's the main force here? It's going to be dispersion. Here. We're looking at formaldehyde, H2CO there, okay? We were looking at it on the previous worksheet. I think it was on there. If you draw this one, the C is double bonded to the O, and you have H and H attached to the C, okay? Don't forget your oxygen would have lone pairs on it as well. However, you could draw it, you could see that it's going to be the trigonal planar type of shape, the planar shape, flat triangle, because it has 3 things attached with no lone pairs on the central atom. However, we need to just look at the ligands. Are they the same? No, the oxygen is different than the other 2. So this one's going to be what type of molecule, polar or nonpolar? This one's definitely going to be polar. And if it's polar, we know it has to be dipole-dipole. Then we look for hydrogen bonding. Do you see any hydrogen bonding here? It has to be H to F, H to O, or H to N. No, because the H is attached to the C here. It is not directly attached to the O. So it has to be directly attached to the O in order for it to be hydrogen bonding in this case. Since it's not, this one would just be considered dipole-dipole or dip-dip. Okay, and last but not least, let's take a look at hydrogen fluoride, okay, which we can draw down here. It's pretty simply. Okay, is that polar or nonpolar? Are they the same? No, so it's obviously going to be not symmetrical or asymmetrical. You can cut it this way. You can't cut it this way because they're different, right? So symmetry's off. So therefore, this one is also polar. Now, looking at it specifically, do we have hydrogen bonding going on? Is it HF, HO, or HN? Yes, it's HF this time. So this one is hydrogen bonding. Okay. Now let's take a look and explain how dipole-dipole forces cause molecules to be attracted to one another. I'm going to use HCl as my example, and we're going to draw it in, and then we're going to use words to explain what's going on. As I drew up there about HCl, you will see here, this side is partially negative with the chlorine, this side over here is partially positive with the hydrogen. If I have another one over here, another HCl molecule, guess what's going to happen? There's 2 of them now. This positive over here is going to attract to the negative on the other molecule. So it's going to kind of stick to itself. I could also put another one down here. Oh, and look what's going to happen. This positive will attract to that negative. This positive will attract to that negative. And all of those red lines here, these are dipole-dipole forces. Okay, they're between the 3 molecules. That's why we call them intermolecular forces. Okay? I could continue to draw this over here. We could continue going with more, as you would see the same thing happening. So this positive would attract the negative, this positive would attract to the negative, and you see it starts this big network of forces holding the HCl together. Okay? So all of those red lines would be dipole-dipole forces. Now, how do we explain this in words if we want to say, how are they attracted to one another? we would say the negative side of one molecule, the negative side of one molecule will what? Attract the positive side of another molecule. Okay, so that's what you would want to write in if you are going to be having to put it into words. Okay? So keep that in mind when you're looking at these examples. If it says explain, this is how you would want to explain it. Okay? Down below here, a couple more quick little things. This one, the stronger intermolecular forces, the tighter the attraction between molecules. Okay? And therefore, the more energy needed to break those forces. So, in order to get something to melt or to boil, you have to break some of the forces. And when you're doing boiling, you completely break the forces to change it into a gas from a liquid. Okay? You need lots of energy to break those forces. So the stronger the force, the higher the boiling and melting points. The weaker the force, the lower the boiling and melting points. So if we look at each of these compounds, we should first identify what type it is. Is it polar, nonpolar, ionic? What type of forces are involved so that we can rank them appropriately. And you will see this type of question on the test. I'm just going to tell you right now. So if we look at our first possible compound here, calcium carbonate, what should we note about that compound? It is what type of compound? What? It's ionic. It has a metal. It has a polyatomic. CaCO3. This one is ionic. Okay? That's the first thing you should have spotted right there. Now, we talked about methane already. Methane is going to be what type of molecule? Polar or nonpolar? All the ligands are H's, right? They're going to attach to the C. What kind of shape we're going to have here? 4 things attached to the C. C gets 8 electrons. It's happy. It's going to be a tetrahedral with 4 ligands attached that are the same. Is that polar or nonpolar? This one would be nonpolar. Good. So therefore, its force is going to be what? What kind of force goes with nonpolar stuff? Dispersion. This one would be dispersion. Now, water we pretty much already know. Water's polar. We've discussed that multiple times. But water has one of those specialized what's in it? Hydrogen bonds, because we have an H to an O. H to O is one of the types. What are the other 2 possible ones in hydrogen bonding? H to F or H to N. You have 3 possible choices for hydrogen bonding. Only those 3. We call it H-bond, having bond with H. Right? No? Okay. Didn't like that one. Last but not least over here, we talked about HCl. We talked about it being what type of molecule? It's polar. Now, does it have H-bond? Does it have bond with H? No, it's not hydrogen bonding because the H is not with F, O, or N. So this one would just be what? What kind of force? Dip-dip, dipole-dipole. So now we have them identified. We have ionic, we have dispersion, we have hydrogen bonding, and dipole-dipole. So we can arrange them from highest to lowest, from lowest to highest boiling points. The weaker the attraction, remember, the lower the boiling point, the stronger the attraction, the higher. So who's the weakest out of those? Which compound? The dispersion one, which one is that? CH4 would be the weakest. Very good. So we're going to use our little less than signs, okay? What comes next? Who's the next weakest? HCl, good. And then comes H2O, hydrogen bondings, and of course the strongest, super strong, is the ionic one, which is calcium carbonate. Good. So you would have to rank them like so on the test. I believe it's also on your study guide to do so. Okay, so keep that in mind. Looking at number 4 here. Explain why nonpolar molecules usually have much lower surface tension, lower boiling points than polar ones. Nonpolar molecules have what type of force? What were nonpolar forces again? Dispersion. So we know that nonpolar molecules have dispersion forces. Okay, nonpolar molecules have dispersion forces. So therefore, we could say they are what kind of attraction? They have what type of force? Weak or strong? They have weak forces. And weak forces mean lower boiling points, lower surface tension, okay? And that's why we would have lower boiling points, lower melting points, that kind of thing. So, that's kind of the notes phase here. Give you a little lead into doing, now we're going to go draw some more dot structures. Okay? And we're going to find the predominant molecular force, and we're going to also identify out of the two who has the higher boiling point. So we've already drawn HCl multiple times. Let's draw it one more time. Okay, and what did we say was the force in HCl? We just did that one. Come on, guys. It is polar, sure, you can note that here, but what was its predominant force there for? It's dip-dip, thank you. Dip-dip. Okay? Now, iodine, we would want to draw it. Remember, I's bring in 7 times 2, so that's 14 electrons, and therefore 2, 4, 6, 8, 10, 12, 14, we've got the dot structure, okay? Attach them and then satisfy the octets around the atoms. And if it had a central atom, you would do the ligands first and then concentrate on the central atom. All right, so what can we say about this guy? Polar, nonpolar, what? Nonpolar, because it's symmetrical. There's only 2 atoms. It's nonpolar. So what would its predominant force be? What goes with nonpolar? Dispersion. Good. So if we're looking at these two here, who is going to have the higher boiling point? The one with the stronger force. Which one's the stronger one here? Dip stronger. So HCl would be your higher boiling point one. Let's do B together. B is a little confusing. And there's a nice big huge methanol structure in it. So, I'm going to draw CH3F. C brings in 4, H brings in 3 because there's 3 of them, and then F brings in 7. That's a total of how many electrons? 14. Who goes in the center? C does. Good. We attach our ligands. Okay, so how many have I used? 2, 4, 6, 8. I have how many left? 6. Are the hydrogens okay with 2? Yes, because hydrogens only need 2. Remember, they're trying to mimic helium. Does the carbon have 8? Carbon? 2, 4, 6, 8 around carbon? Yes. Good. Who's not satisfied? Fluorine does not have, fluorine only has 2 here. So what do we do with the rest of those 6? Put them around your fluorine, right? That's how we would draw that particular structure. Now looking at it, so we have 0, okay? Is that polar or non-polar? Are the ligands the same? No, the ligands are not the same, so therefore this is polar. So, but now let's look at the bonds. We have H's and F's in here, so we have to be very careful. We have H to C when we have F to C. Do we have any H to F's though? No, so this does not involve hydrogen bonding. So this one would just be what? What is the polar one? Dip-dip, dipole-dipole. Okay, now we have that one done. Let's look over here at our methanol, which is CH3OH, like that. All right, so I'm going to put the numbers over here on this side. We have C that has 4. We have H's that there's 4 of them, so that's 4. And then we have one O that's 6. How many electrons do we get to deal with? 14, right? 14. So, who's going to go in the center? This time we're going to have 2 things in the center. C is going to go in the center, and who else? Oh, because we know hydrogen can't go in the center at all, right? Now, how many bonds can oxygen form? Remember over here, oxygen, how many bonds can it form? 2. So how many can we really attach that? Only 2. So let's start putting our hydrogens, and it says H3, so these 3 really belong on the C because they're connected to the C there. See how it's H3? Those 3 should go on the C, and then the other H over here should go off of our oxygen, like so. So now we've attached our ligands. So we've used 2, 4, 6, 8, 10 electrons. We have 4 left. Who still needs 4 electrons? Oxygen does. That's nice and convenient, because guess what? We have 4 to give the oxygen. Okay, so that would be the Lewis dot structure for methanol. Now looking at it, is it polar? Yes, it's definitely not symmetrical. If you were to, go down the center here, not symmetrical at all. No symmetry. So, looking here though, does it have bond with H? Oh, look, yes, we have an O to an H bond here, right here, an O to an H. So this one has what? Hydrogen bonding. Okay? Now, looking at our 2 and comparing them. Dip-dip with hydrogen bonding. Who's going to have the higher boiling point? Who's stronger? Hydrogen bonding. So therefore, over here we would write in methanol. I'm going to skip down and do a couple down here just for fun, for you to recall. Like this one, HBr with krypton. Krypton's one of those noble gases that doesn't like to bond with anything because it's already stable on its own. How would you draw krypton? How many valence electrons does a krypton get? 8, right? So all we have to do is put 4 pairs around it. Right? Not hard. You can do that. All right, for HBr. HBr is very similar to HCl, right? Because Br and Cls are both halogens. So what would we put here? We have 1 from the hydrogen, 7 from the Br, total of 8. We already used 2 by attaching them together with a single bond. So where do the other 6 go? They go around the BR. 2, 4, 6. Very good. Now, is this guy polar or non-polar? Definitely polar. Atoms are different. So, do we have bond with H? Any hydrogen bonding there? H with F, H with O, or H with N? No. So this is just going to be a dip-dip because it's only polar without hydrogen bonding. Over here, does krypton have an electron cloud? Yes. Does krypton bond with anything? No. But can I sidle up to a krypton with my electron cloud and displace it a little bit? Sure. So krypton can do a temporary dipole. So that would be what type of force? Dispersion. Correct. So that would be dispersion. Out of those two, who's stronger? Dip is stronger, right? So, therefore, HBr would have the higher boiling point. One more fun one to do. We already did methanol, so we can redraw that very quickly. And we already know that it's polar because we already identified it up there. So we know that this guy has hydrogen bonding because we've already done it. Okay, but now we're going to compare it to copper 2 oxide. What does that tell me automatically? Copper 2 oxide. It has copper in it. What kind of compound would have copper in it? What type of element is copper? It's a metal. Good. So it's automatically going to be, who has metals in their compounds? Ionic. Good. This is ionic. However, we still have to draw it. How do we draw ionic compounds when we're doing dot structures? Well, we would need to figure out the charge on copper to know how many electrons it actually gave away. What is the charge on the oxygen? What does oxide go to? Group 16, what charge? -2. This goes to -2. So that means the copper has to be a +2. So we know the copper is going to give away 2 electrons. So I'm going to give the copper 2 dots. How many does the oxygen start out with? How many valence electrons does oxygen have? 6. So we start out with 6. So the copper is going to give away its electrons. Remember this? This was like way behind back then when we first started. So the copper ends up being a +2, and the oxygen has 8 dots with a -2. Don't forget to learn, remembering how to draw your ionic compound dot structures. Okay? Out of those two, though, who's stronger? Hydrogen bonding or ionic? Ionic is. So therefore, our copper 2 oxide would be the correct choice for the higher boiling point. Alright. Now let's look at the last one on the other side. Another nice little flow chart for you to follow to determine what you're dealing with. You can go up here. Are the atoms in the molecule identical? Yes. Then it's dispersion. No. Is it polar? If it's not polar, it's automatically dispersion. Here we go. Is it polar? Yes. Is one of them hydrogen? If the answer is no, you go down here to dipole-dipole. Okay? If one of them is hydrogen, does it have bond with H? Is it with F, O, or N? Okay? If that's a yes, then you go over here to the hydrogen bonding. If it's a no, you go back up to dipole-dipole. If it's a no, you would go that way. Okay? So follow the lovely flow chart for help. So down here, I'm just going to do a couple before you go. Looking here, it even gives you the shape to help you. Tetrahedral, 4 things attached. That means this one's going to be nonpolar. Nonpolar automatically tells me it's dispersion. If I'm looking here and it's bent, bent tells me automatically what? It's going to be polar because it has lone pairs. Does that have any H's in it to begin with? No H's means it's just going to be dipole-dipole. Dip, dip. Okay? So follow the chart here and make sure that you are doing this. I'll do number 17 over here. Trigonal pyramidal. When we have ammonia there, that has a lone pair, so that tells me it's going to be what? Polar. Now, is it having bond with H? Because H is in there. Yes, it is. H with M count. So this one would be hydrogen bonding. Finish that up for homework. Be prepared for your quiz on Tuesday. Have a good day.